In November 2000, at a hospital in Panama, 28 patients seeking treatment for cancer received massive overdoses of gamma rays from a medical machine. 5 of those patients died from radiation poisoning, and 15 others suffered severe complications. Investigators looking into the tragedy found no mechanical defect in the medical equipment. There was no human error on the part of the hospital staff. The device failed because of poorly deployed, invisible computer code. While the Panama incident is an extreme case of physical harm, the underlying issue scales across the entire global economy. Defective code accounts for roughly 45% of computer system downtime, costing U.S. companies an estimated $100 billion a year in lost productivity and repairs. It is a phenomenon known as the software crisis. A Capers-Jones study broke down 250 large software projects. Only 25 successfully achieved their schedule, cost, and quality objectives. Meanwhile, 175 experienced severe delays, extreme cost overruns, or were canceled. We rely on computer software to operate our financial markets, our power grids, and our medical devices. Yet, statistically, the baseline state of a large software project is catastrophic failure. A major reason we struggle with software is that we expect it to behave like the physical machines we used to build. Traditional hardware follows the bathtub curve: early failures from defects, a flat line, then rising as parts wear out. Theoretically, software curves drop and stay flat forever. But code is malleable. Every update introduces new errors, causing sharp failure spikes. Computer programs don't break down from vibration or rust. Software deteriorates precisely because we never stop modifying it. That constant deterioration carries a massive financial penalty. When a team creates software, the cost to fix an error depends entirely on when they catch it. An exponential growth chart tracks the cost of a single bug. Fixing a defect during the design phase costs around $139. Finding that exact same defect after release costs over $7,100. Developers know this, yet the pressure to hit strict market deadlines is often so intense that companies will knowingly ship buggy, good-enough code just to get the product out the door on time. Treating code development as a rush job locks a company into those late-stage repair costs, guaranteeing massive financial losses and a high risk of critical system failure. The financial data explains the cost, but the collapse of a digital project usually comes down to human psychology. For decades, programming culture has operated on a specific set of flawed assumptions. Industry professionals have a running joke called the 90-90 rule. It states that the first 90% of the code takes 90% of the scheduled time. The remaining 10% of the code takes the other 90% of the time. When a schedule slips like that, project managers often invoke what is known as Brooks' Law. They look at a late project and instinctively assign more programmers to the team to catch up. Adding people to a late project actually delays it further. The new team members have to learn the system, which means the original developers have to stop writing code to teach them. Every new person also creates a new line of communication, heavily increasing the logistical overhead. As deadlines loom and pressure mounts, the intuitive decisions made by managers, like adding staff to a delayed timeline, act as accelerants, pushing struggling projects into total collapse. Building reliable code requires abandoning the idea that programming is an ad hoc art project, or that it can be managed like a traditional manufacturing line. To manage this specific type of digital complexity, the industry developed a rigorous discipline known as software engineering. Instead of jumping straight to writing code, this framework prioritizes heavy upfront communication with the customer. It demands precise project planning, formal modeling of the system architecture, and strict peer reviews before a single line of code is finalized. By forcing a team to catch defects during the initial design and modeling phases, this discipline actively flattens out that escalating cost of change curve we looked at earlier. To prevent billion-dollar financial drains and dangerous physical failures, the technology sector has to stop treating end users as live beta testers. We have to engineer the digital world with the exact same rigor we apply to the physical one.